Dewatering is quite a popular way to improve the ground for any geotechnical works. So I want to spend a bit of time on that. There were some questions raised by students afterwards regarding the differences between piezometer and standpipe. This is a common misconception that these are the same instruments. These are also very common interview-related questions where they ask you what's the difference between a piezometer and a standpipe, what you're measuring. So this is fine. It's all part of the story of dewatering anyways. So I never showed this overall Bernoulli equation in the last couple slides. This is not in your notes. I can put them back up here. So there are in essence three components to any flow problem. If you want to understand dewatering, you have to realize that flow is governed by total head, right? What do we mean by total head? Well, there's three components. We have velocity head, pressure head, and elevation head. We understand these principles from our fluid mechanics class and also from rudimentary soil mechanics. Now, if you remember from your soil mechanics class, the velocity in soil is relatively slow. Soil is relatively, has a low permeability as a porous media. So it's common to neglect velocity head because it's quite small compared to the other two components, particularly elevation head and pressure head. You often see in the literature or even in industry numerous terms being used. For example, total head may be referred to as hydraulic head. When you see the word piezometric head, what are we referring to? Well, sometimes they refer to the combination of pressure and elevation head. So I hope this is a review for you. In case you've forgotten, that's fine. We can talk about it here for a bit. So this is the basic Bernoulli's equation that governs flow. When we dewater, we want to promote flow from high to low total head. Now, the common misconception about common instrumentations to understand groundwater monitoring relates to two instruments that we use. The first is a standpipe, and the second is a piezometer. Often in industry, you might see that we mix up the term, and we might even call it a standpipe piezometer. Well, at least you understand that these are two different instruments. They might be referring to standpipe piezometer combination, where you have a piezometer and a standpipe installed side by side with each other. The reason is we want to save money by only drilling one borehole and installing two instruments next to each other. If you're asked what's the difference between a standpipe and a piezometer, well, let's take a look at fundamentally how these look like. Anything related to dewatering requires us to have information about the response of the ground, particularly the groundwater. What are the piezometric pressures? Where's the water table? We need to know this information when we're carrying out dewatering for ground improvement. Standpipe on the left here is in essence a perforated pipe all the way from the top to the bottom. This allows water to move in and out freely along the entire elevation of the pipe. If you look at the schematic here, you see holes here, or the dots are essentially perforations. And what the perforations enable with depth is for the groundwater table to equalize. If you use a standpipe in the field, you will be able to detect the groundwater level, or the surface of the water table in the ground. That's the information that it gives you. Notice that typically we install this perforated standpipe surrounded in a pervious gravel layer, which is purely for filtration purposes. More often than not, we often line the perforated pipe with some sort of geotextile to minimize infiltration of fines into our standpipe. We'll talk about how to use a standpipe, how it looks like, and also a piezometer in the following slides. At the top of a standpipe, we often put concrete plugs. This is to prevent the infiltration of surface runoff into your standpipe, which can affect your readings when you take it. So, if you can guess, you can probably surmise that standpipe may only be good for detecting the water table level. If you switch to the right of the slide now, and we look at the piezometer. Sometimes in industry we call it standpipe piezometer. I'm not sure if that's a misconception or they're referring to standpipe piezometer combo, as I just mentioned, but the difference with the piezometer is that notice that we don't leverage the full perforated or perviousness of the pipe here. For the same elevation, we can assume that the piezometer is nearly at the same elevation as the standpipe. We've actually grouted this top part of the pipe. What does that mean? Well, it means that unlike the standpipe, where water can freely move in and out of this pipe, in this case, the piezometer, the water cannot move in where the pipe is surrounded by grout. The water can only move in near the bottom of the tip of the piezometer. We often put a filter tip and also gravel to minimize the effects of fines causing well resistance, and we also have bentonite seal at the top and bottom so that we have a very localized reading. With the piezometer, we want to understand what the pore pressure is at a local position in the ground. We only want to know what the pore pressure here at this elevation. So the piezometer is an instrument that provides a local measurement of the pore pressure in the ground, whereas a standpipe only gives you indication of the free surface of the water table. If you look at the surface of the groundwater table here, outside the piezometer, you can see that it's quite different than that deduced inside the piezometer. It can be lower, right? It can also be higher. It depends on how groundwater is moving. Is it moving away or towards, right? We'll look at these examples later on. So, just based on a comparison between a standpipe and a piezometer, you can probably guess that this piezometer will not give you an indication of where this groundwater table is. It'll give you a localized pore pressure reading at a very specific elevation. So if you want to know the pore pressure at different elevations in the ground, you need to install numerous piezometers with tips at different locations. So if I want to get the pore pressure profile, let's say with depth like this, then I would need to install separate piezometers with tips reaching those locations. So that's from a very superficial point of view, from how the instrument looks like. That's the fundamental difference between a standpipe and a piezometer. But we'll go look at this in a bit more detail before we talk about dewatering again and how we leverage dewatering for, let's say, coffee dam problems. To give you a bit more indication about how standpipes look like, we mentioned that it's a perforated pipe, so you essentially have holes along the entire pipe. As you can see here, here's the real perforated pipe, and often we place filter fabric around it. The filter fabric is quite pervious, but the main purpose is to minimize the migration of fines into your standpipe so it gets clogged. If it gets clogged, you're not going to get proper groundwater measurements. Here is an actual detailed engineering drawing of what we call an observation well. And you're wondering, what's the difference between an observation well and standpipe? Well, a standpipe is an observation well. It's called observation well because it enables us to observe the free surface of the water table in the ground. So often for construction sites, you'll see terms such as O-wells, which stands for observation wells. You can also have D-wells, dewatering wells, where you put in the pump, and so forth. So here are three schematics of a standpipe, and just like we talked about, we have a very long segment of a perforated region that enables the groundwater to equalize, and at the top of this observation well or standpipe, it's heavily grunted with concrete plugs to minimize infiltration from the surface. If we can minimize infiltration from the surface, this will help minimize problems when we're taking measurements if there is heavy rainfall and lots of surface runoff. So this is how a standpipe can look like. If you want to measure the groundwater table inside a standpipe, it's quite easy. We often have instrumentation technicians on the site carrying around what we call a dip meter. It's nothing fancy, essentially a tape, measuring tape with an electrode at the tip of it. So if you know the elevation of the tip of your observation well or your standpipe, you throw down this measuring tape, and when you hear a loud beep because the electrode touches the water surface, then you know this is your free surface of the groundwater table. So it's quite simple. Essentially, dropping this down and you know the length of the tape, and that's how you measure your groundwater surface, often in meters principal datum in Hong Kong, or MPD. Here are more pictures of perforated plastic pipes with geotextiles wrapped around it. So this is what I refer to as a standpipe, or in this case, an observation well. So let's look at how these two types of instruments differ even from a more fundamental level. Now, we have three cases on this slide, cases A, B, and C. In case A, we have a hydrostatic condition, which means there's no flow in the ground, everything is static. So let's just focus on case A for the time being. If you remember from Bernoulli's equation, we have elevation head, and with elevation head, you need some sort of datum, a reference level. So, and this can be arbitrary, right? Because it's all relative to each other. In this case, our datum, our reference level, is just located at the base of this piezometer, or instrument. So for case A, if you have no flow in the ground, your standpipe and your piezometer should, in principle, give you the same elevation, right? It's only if you have flow in the ground where you'll see differences between the water level inside your standpipe and your piezometer. In case A here, everything is static and not moving, so you have static groundwater level, which is H subscript W. So that's your hydrostatic water head relative to your reference line, reference level, or datum. Now, what happens in case B? Well, in case B, if I delete this for a sec. In case B, if you focus at the bottom now, we have some sort of flow in this direction. So in this previous case, we didn't have an arrow that's blue with two arrowheads, so this denotes flow. When you have flow on the ground, what happens to the water level inside your piezometer? Well, it would decrease, right? Based on your understanding of flow nets and seepage from your soil mechanics class, this is just a quick reminder, you would have a drop in your piezometric head, right? So inside, this is not a standpipe, this is a piezometer, okay? So it's not perforated. And you can see that there's a difference between HW and HW1. With flow, you can detect the water level in your piezometer to decrease. Now, think about this from a geotechnical point of view. What use is this to us as geotechnical engineers? Well, if you have a standpipe right beside a piezometer, so we call this perhaps a standpipe-piezometer combination, then you can detect movement of water in the ground. Why is this important? Well, I'll talk about it in a bit. When we look at pumping tests, cofferdams, where you're trying to achieve hydraulic cutoff in the field, you need to deduce whether you're still getting flow inside your cofferdam. That's why we have standpipe piezometer combinations. So this case B here, you have water flow, and if you have water flow, there'd be a decrease in pressure corresponding to whatever your change in pressure parameters, right? So that's case B. Now, case C here is a bit different. Let's say you have reduced outflow here. If you have reduced outflow, notice that this will actually increase inside your piezometer. So let's say there's some sort of outlet blockage, you'll see some sort of buildup. Now, if you have a standpipe that's perforated, you may not necessarily see such localized changes because the flow could be very local in the grand scheme of things, and the recharge rate from your surrounding environment could be very high relative to these local movements in the ground. So if you want to detect locally whether there's flow in your cofferdam, then it's ideal to use standpipe and piezometer combination. So if there's flow away from your piezometer, you'll see a drop. If there's some sort of blockage or you have a successful cutoff, then you'll see your groundwater table move up inside your piezometer. So these are in essence the three cases that you'll see for piezometer. So let's take a look at this problem in a bit more detail. So let's say we have a big aquifer here in the ground, in this blue. It's a giant bathtub. The question is, what are the differences among locations 1, 2, and 3 in this diagram? Well, let's look at this diagram at the top here. So we're assuming instant recharge. We're assuming that anything that goes out here is nearly inconsequential compared to what's recharging. So when would this play out? Well, if you're constructing something right beside the ocean, which is quite common in Hong Kong, right? Any coastal structure, Western Kowloon Terminus Station, you're literally right by the sea. So your recharge, even if you're pumping or dewatering water, is nearly instantaneous, right? So if it's instantaneous, your recharge, how do you detect localized changes of flow inside an excavation? Well, then you rely on piezometers. So if you look at case 1 here, we can assume that this is a piezometer. There are no perforations here. Unlike case 3 here, you see there's perforations, right? There are holes in this pipe, but in case 1 there's nearly no perforations in the pipe, so it's a piezometer. And where is the groundwater level? Well, it's exactly where the top of the reservoir is, which is fine. Case 2, however, is also standpipe, but we see a drop in the piezometric level. Why is that? Well, locally, there's flow in that ground at this particular elevation. If you had standpipe number 3 installed beside number 2, you won't see this subtle drop unless you had a localized piezometric pressure measurement. So that's why in the field we often we refer to these as perhaps SP or standpipe piezometer combinations. Within one borehole we install both. For example, the standpipe number 3 would be useful for indicating where the water table is if you're trying to draw down the entire water table. Conversely, for piezometer number 2, if you have the entire pipe sealed except for the tip at a particular elevation, then you can look at if there is flow inside the ground at that particular elevation. And we'll talk about the practical applications in terms of dewatering of using these instrumentations. So at location 1, the water level will be the same as the water tank. We assume that there's constant or instant recharge because we're adjacent to the sea. At level 2, the water level will be lower than that in the tank because we have localized outflow at this location. And you can imagine this could be a diaphragm wall, right? This could be the passive side of excavation. You're getting some sort of flow net moving into your excavation, for example. Location 3, the water level inside the perforated pipe will still be the same as that of the tank because it's perforated and allowed to equalize. So this is an example of how we leverage standpipes and piezometers for dewatering indication later on. So, practically, how do we use these concepts for dewatering? Well, we often in the field, as I mentioned, we use SP combinations, which are standpipe piezometer combinations. This means that if we look at a particular case here for cofferdams, all of your FYP projects have probably a cofferdam, right? Anyhow, so let's look at the first case. We have essentially some sort of wall. It can be a sheet pile wall, can be a diaphragm wall if you have a lot of money. But essentially what you want to do is, you notice that the water table outside is up here, the water table inside is down here. And we just assume that this is due to some very successful dewatering. So there was some pumping action taking place before that enabled us to draw down the groundwater table inside your excavation, your passive side of your excavation, and enabled you to maintain some sort of groundwater table like this. Now, at the bottom of the excavation wall, we have something interesting here. This is what we call a grout curtain. Why do we call it a curtain? Because we assume that looks like a curtain underneath your diaphragm wall. And often we install a curtain all the way along the toe of the diaphragm wall if we want to enhance hydraulic cutoff. There are some structures in Hong Kong that require 100% hydraulic cutoff. For example, if this was maybe say a metro station, we can't have water coming into the site. And if we didn't have this concrete grout curtain here, which we'll talk about when we get to grouting, you can imagine that you'll have some sort of flow net like this. And if you turn the pumps off, you won't be able to suppress the groundwater table, and your groundwater will equalize, and inside your excavation it will be buried. More often than not, I don't think for some projects you can continuously turn on pumps, right? Eventually you have to get a pretty good hydraulic cutoff using any means to just block the migration of water from the active to the passive side of that excavation. So let's say in this case we have a grout curtain, and the grout curtain is very successful underneath the toe of this retaining wall, and we achieve exactly what it says here, 100% effective water cutoff. So essentially when you have 100% cutoff, what does that mean? Well, the groundwater table outside of the excavation and that inside the excavation are hydrostatic. There's no movement. If it wasn't hydrostatic, there'd be seepage into your excavation. So the pore water pressure, you can easily estimate it, right? You can see these yellow triangles are in essence unit weight of water times some depth. Z here, likewise, if you want to call this Z, this is some unit weight of water times Z. It's very easy to calculate the hydrostatic water pressure for these cases. And what does this mean relative to standpipe and piezometer combinations? Well, you can see that if you install this kind of combination, let's say this was one borehole, you have P for piezometer, S for standpipe, and remember that the standpipe is fully perforated with depth, while piezometer only gives you a localized reading at this particular elevation. If you're hydrostatic, what happens? Well, the elevation is the same inside your piezometer and your standpipe. There's no difference. And right now it's hydrostatic because we mentioned this is a very good cutoff. Unlikely, for most cases, it's difficult to have a very good curtain, right? Now, let's look inside the cofferdam here. So, inside the cofferdam, since we achieved 100% effective hydraulic cutoff, the passive side is also hydrostatic. If it's hydrostatic, what do we expect? Well, we have a standpipe piezometer combination again. Standpipe is entirely perforated with depth. Piezometer only gives you a localized reading here, and we can see that we're getting the same elevation. So if you are a geotechnical engineer on site, this doesn't have to be for cofferdams. If you have these combinations for a slope, you can also detect the migration of water, right, if you have piezometers. But this is just a very simple concept on how to leverage standpipe piezometers. If you understand the concept here, you can apply it to any geotechnical infrastructure, embankments, dams, and so forth. So this is a very idealized case on the left side of 100% hydraulic cutoff. Now, let's take a look at this case here. For the case on the right, we have an ineffective water cutoff. What does that mean? Well, it means, if you look at this little red circle here, this grout curtain, it wasn't done so well. We're getting some movement of water right through this so-called grout curtain anyways, at the toe of the diaphragm wall. It's not ideal if the ultimate goal is to get 100% cutoff. What happens from the groundwater perspective? Well, let's take a look at the active side and the passive side. So outside, on the active side, we can see that, like the example on the left that I showed you for 100% hydraulic cutoff, we have a piezometer and the standpipe combination again. Now, only in this case, we're not hydrostatic because evidently there's flow at this particular location, and we know that water moves from high total head to low total head, so the groundwater must be moving from outside to inside your excavation. And if you did not have a nice dewatering well here, suppressing this groundwater table here, let's say we turn off a pump, we would likely see the rise of this groundwater table until it reaches hydrostatic conditions with that on the active side. But let's say we have a pump that's running inside the excavation, it's keeping the excavation dry and the workers inside the excavation safe. Now, if that's the case, then let's take a look at how the pore water pressure instruments look like. So if there is flow, just like I showed you with that reservoir example, notice that your piezometer, which gives you a localized measurement at this point, drops relative to the standpipe. The standpipe here is more or less the same as the 100% cutoff case, right? You can't really detect these small movements in the ground, right? Unless there was a massive hole in your grout curtain, and maybe you'll see a massive drawdown like this, but it's unlikely, right? Because that would be a catastrophic failure of your excavation, which would be quite alarming. So in most cases, you would perhaps see just a slight dip here in your piezometer compared to your standpipe. So as a really strong geotechnical engineer, you would realize that there's probably some sort of migration or flow in the ground. Now, how does the pore water pressure distribution look like behind the wall? Well, we would see a hydrostatic profile look like this, but you would see some alleviation of pore pressure effect on the wall where the flow is. That's essentially how it works. And on the passive side, likewise, we have flow now moving into the passive side of excavation. We have standpipe and piezometer combinations. In this case, we see the opposite. It's not really a blockage, as in the reservoir case in the previous slide, except you might see in the piezometer an increase in the piezometric head relative to that in the standpipe. Standpipe still gives you a really nice indication of where the free surface is, but the piezometer will give you a localized pressure reading just at where the grout curtain should be. And if this right here shows a drop in the piezometric head, and the corresponding location inside your excavation shows an increase in piezometric head, this is a telltale sign that you haven't achieved 100% hydraulic cutoff and you're getting flow inside your cofferdam. So that's how we would use these standpipe piezometer combinations. So this is just one example of how to use standpipe and piezometers. Now, often in dewatering scenarios, we carry something called a pump test. I'll talk about what that is in a bit, but let's cover a few more scenarios first. Why is it important to consider total head, right? Because there are circumstances where, if you recall, there are unconfined and confined aquifers where you would actually see the water level even come out of the ground, exceeding that of your instrument, your piezometer or your standpipe. Now, if you look at these instruments here, these represent tips of instruments. I'm guessing these are piezometers here. And if you look at the geology of this particular diagram, it's quite interesting. You have something at a higher elevation head, essentially creating a gradient here. And the water that travels inside this piezometer would likely want to equalize to some height here. That's why you get an outflux of water at this piezometer. We often refer to this as artesian pressure. So that's what happens if you have a piezometer with its tip installed inside a piezometer, or inside a confined aquifer. You can also have just the most simple case where you have the tip of your piezometer here on some perched water table, where it just sits on top of a piece of relatively impervious material. So in this case, this is, let's say, clay, and the water would just sit on top of this piece of clay here. This can be misleading, right? If you don't realize that this is a perched water table, and you think that this is actually the water table in the ground in a very continuous geology, then you might get a misinterpretation if you're designing some sort of geotechnical structure. Because if this instrument was to be installed further in the ground, you'll realize that what you measured there is just a perched water table. It's quite shallow. Of course, you can see other cases where you also have confined aquifers, and you can also, in this case here, you would just get a nice water table measurement here, probably not too much artesian pressure. In this case here, you would just see the artesian pressure coming out here. You would probably bypass the water table here. So depending on where you install your piezometers, the lesson of this slide is confined and unconfined aquifers can greatly disrupt your readings. You can have perched water tables, confined and unconfined aquifers giving you misleading measurements, because at the end of the day, piezometers are very limited in that you can only measure what you get at the tip of the piezometer, right? So in these cases, it would be useful to have a standpipe in combination with piezometer, so you can have a much more in-depth interpretation of how underlying hydrogeology is affecting your decisions as a geotechnical engineer. So that's all I want to talk about the limitations of installing piezometers at the wrong height. Now, we haven't shown you what a piezometer looks like. Well, this is how it looks like. If you want to install on the ground, we have a very pervious tip. The top here is impervious. You have filter paper along, and you can install this with bentonite at the tips and the top, so around here and around here, so you have very localized reading when you insert it into the ground. And we talked about geosynthetics. Normally we would wrap the tip with some geosynthetics so you don't get fines washing in and clogging up the piezometer. It's very common for piezometers to be clogged and need to be flushed. So bear in mind that in the classroom it seems very easy to get very good piezometer readings. After a construction project has been going on for a while, it's very common for a lot of your piezometers and standpipes to not function because of well resistance, cloggage from fines, and the filtration system is not working. You can see that there are some advantages and disadvantages listed for this type of instrument. The disadvantages we somehow talked about. It really is dependent on what elevation you put the tip of your piezometer. Piezometers can have very slow responses as well, so if you want an instantaneous response or measurement, it may not be such a good instrument. You might be better off using maybe a vibrating wire piezometer, for those of you that have heard about it. You also have to take manual measurements, and it can be time consuming. So this is how a Casagrande or open hydraulic type piezometer looks like. These are just other names for this particular device. And the typical installation procedure would be, you have to drill a borehole here. And as I mentioned, drilling boreholes can be expensive, so it's common to install both a standpipe and a piezometer in the same hole. We would lower our instrument in whatever pipe we like, lower a tremie pipe to the bottom of the hole, and then you drop in some grout. It can be coarse material, gravel first around the tip. You can also use bentonite pellets to seal off the top and bottom of a piezometer to improve your readings. That's what bentonite chips are, essentially clay. It's bentonite, right? So it provides a seal, localized seal here, and then you can fill it up with, in this case, grout all the way to the top. And here you have sand or gravel acting as a filtration, naturally using soil, and you can get this type of measurement. So this is the general procedure for standpipes and piezometers. For piezometers, yes, use the bentonite and the localized installation arrangement, but for a standpipe, you would use mostly gravel or sand along the entire depth to leverage the entire perforated length of the standpipe. So this is how these instruments are installed. So in case you're wondering how the bentonite looks like, so these are the bentonite materials. You can just rain in at the top, and if you want gravel or sand around the tip, this is what we place around the tip of the piezometer or around the standpipe. There's also another instrument that we use in Hong Kong that's quite interesting. You can probably imagine a standpipe. If you wanted to, let's say you're designing a slope, and you wanted to know what the maximum water table was. Unless you're at the site 24 hours, 7 days a week, you might miss a rainfall event or how high the groundwater table was in a particular standpipe or piezometer. So what can we do? Well, there's something called a Halcro bucket in Hong Kong. Halcro bucket are in essence a series of buckets on a string. You can see it being lowered down in this hole here. What happens if this is your normal groundwater table, and then let's say there's a very large rain event. Now, when we design slopes, for example, we want to know the maximum groundwater table experience because we know from geotechnical knowledge that we want to design for the most extreme case. And the higher groundwater table means less stable your slope is, right? So if we're not on site all the time, or we don't have real-time measurements using vibrating wire piezometers, or pore pressure transducers connected to data logger that's constantly taking data, we're going to not be able to see this peak. So then we use something called the Halcro bucket. So what happens if the groundwater table suddenly rises due to a very large rainfall event, but we're not on site at that time? Well, what happens is, after the groundwater table goes back to normal, recedes, and you come to site, well, you'll realize that, look, these two Halcro buckets are full of water. So you know at least the groundwater response was up to these particular elevations. Now, of course, how fine are the readings? Well, evidently the groundwater table is up to here, but you can only surmise that from the Halcro bucket, the groundwater table reached this height. This is still better than no information about the peak level of the groundwater table in your standpipe or piezometer. So that's what we refer to as Halcro bucket for those of you that have worked with instrumentation monitoring for geotechnical projects on site. And I talked about another type of fancy instrument called the vibrating wire piezometer. This gives you real-time measurements. We won't talk about the principle of it, it's more complex, but you get continuous, near real-time measurements of the groundwater response. You connect a data logger, you'll get lots and lots of data time. You can get the pore pressure response easily. So, some other salient points to worry about for standpipe and piezometers. You have to really trust the person taking the readings. More often, these are technicians that have measured a lot of standpipes and piezometers with time, and some of these readings could be influenced by runoff into the top of your pipes, and this can give you very misleading readings. So this is one thing to be aware of. That's why we seal the top and we have covers to minimize the effects of surface runoff on our readings. So this is just one precaution to bear in mind. Now, I sort of sidetracked a bit because I got a series of questions from students not understanding how standpipes and piezometers work. So I think it's important to cover that. So that's how standpipes and piezometers work. If you're asked what's the difference, now you know. Back to dewatering. So the essence of dewatering is to pump down the groundwater table because we want to increase vector stress, or we just need to temporarily get into an excavation. And I talked about some of these points already. So essentially we're installing pumps at different elevations, different types of pumps, centrifuge, pneumatic, electric pumps, sump pumps, anything we can to suppress the groundwater table. Advantages of dewatering, extremely simple form of ground improvement. In terms of calculations, probably not much you need to do for interpretation, except you might need to design how many pumps you need to potentially suppress the groundwater table. Even your design may not work based on field conditions, but it's quite simple, and reducing core water pressures in the ground can strengthen your ground significantly. Limitations. This is a common problem with dewatering. You need to carry out sensitivity analysis. For some of your FYP projects, I remember on Friday, one of our industrial tutors asked whether you calculate the subsidence outside of your cofferdam. Well, often, as we mentioned, if you have a cofferdam like this, and you want to suppress the groundwater table, let's say this is the initial groundwater table before you carry out any construction work. In a very idealized case, you can sort of maintain this groundwater table. But what if you turn on a few pumps here, and this starts to get sucked in, then your groundwater table outside the cofferdam decreases. And if you remember from our consolidation lecture, this causes consolidation, and it can cause settlement infrastructure outside. If you have, let's say this is a gas main that's sitting on some sort of footing inside the ground, you can cause the mains to dislocate, right? So the pipes are connected by joints. So if you have localized setting, then you have dislocation of utilities. If you have infrastructure at the surface on some sort of footing, this can also cause settlement around your construction site. So dewatering requires you to calculate the subsidence from drawdown. If you can calculate how much you need to draw down outside relative to inside excavation, then you can consolidate. You can calculate the consolidation in terms of settlement. Often than not, Plaxis may only give you settlement due to deformation. When we calculate the excavation sequence, we expect something like this, right? Settlement here. But this is only due to soil structure interaction. If you also have a drawdown sequence of your groundwater level, you also need to calculate what's the effect of drawing down the water outside by 1 meter, 2 meter, 3 meter, and you need to add these settlements together. And if you have some threshold like 25, 20, 15 for AAA system, for example, then this needs to be catered for when you do your sensitivity analysis. So that's what we mean by potential ground subsidence causing damage to adjacent infrastructure. There are also other factors to consider for a pumping test. Normally, before, let's say we installed 2 sheep piles and we plan to excavate in the middle. Before we excavate, we often do something in Hong Kong called a pumping test, or not just Hong Kong, the geotechnical industry at large. What is a pumping test? So let's say we install some pumps. We've seen some pumps here. sink a few pumps like this, and before we excavate, we can do a pumping test. And this is to check whether we can suppress our groundwater table. So this is a D-wall, okay, D-wall, or diaphragm wall, or sheet pile wall, whatever you like. So let's say the groundwater table is initially hydrostatically like this, but we need to get to final formation level in the ground, let's say here. So that means we need to somehow suppress this groundwater table to perhaps some elevation below the working elevation, so we can work and have machines inside. Otherwise, the excavation will be submerged. So before we even excavate inside this cofferdam, this is side view, by the way. Before we excavate this cofferdam, what we do is called a pumping test. And the pumping test, in essence, we install a lot of, let's say we install, I'm just calling it SP combination, okay? There are two pipes. Different SPs around the site. And this is just a side view. So if you have a plan view, if you have a rectangular cofferdam, then you need to install these at systematic locations. These are SP combinations around your site and also inside your cofferdam. And you need to monitor during a pumping test. So what do you do during a pumping test? Well, you turn on these nice green pumps. Turn them on and see what happens. And let's say we turn it on in this example. Well, let's say the groundwater table does is somehow suppressed to this new profile here, something like that. So let's say we're able to draw it down. So the point of the pumping test is to make sure, did we install enough pumps? Often, if you do calculations, seepage analysis, you might put in, let's say, 4 pumps, but you realize even 4 pumps is insufficient because we make a lot of assumptions in the permeability of the soil. During the ground investigation, we drill limited boreholes, so we may not understand the entire geology, right? And 4 pumps may not work. And then during your pumping test, let's say you cannot suppress the groundwater table, then you need to install more pumps. And you need to look spatially around this pumping test site. Are there enough pumps in certain locations? Are some locations really pervious? So let's say there's an inability to draw down the groundwater table here because the recharge is too high. This may be indicative that your sheet pile wall has a huge hole in it, right? Sheet pile walls rely on the mechanism hooking each other, each component, right? There could be a gap, maybe there's a core stone, and there's a huge hole in your cofferdam. So the sheet pile, the pumping test is 2 functions. The first function is to make sure you can draw down to the safe working elevation. That's the first function. The second function is, what happens if this malfunctions, what's the recharge rate? It's common for pumps to malfunction. Will your entire cofferdam recharge too quickly so that whoever's working inside doesn't have time to evacuate? So there's 2 main functions, remember that. The first function is, can we draw down to the expected working level? Number 2, what's the recharge rate? And number 3 is, I mentioned it earlier, sorry, there are 3. What's the subsidence caused outside? Was there any settlement? So besides purely looking at SP combinations, you probably also have settlement markers outside to detect if you're getting ground subsidence purely from drawdown. So this is what we refer to as a pumping test. So any cofferdam inside a place that we need to dewater, we carry out a pumping test to do 3 things, as I mentioned, and I'll mention it again. First is, can we draw down to the required water level, number 1. Number 2, is the recharge freakishly fast, so we can't get people out. Number 3, what's the potential consolidation or subsidence caused outside of your excavation? So these are some things you need to consider when you carry out dewatering for cofferdam. So I think I'm out of time. We'll carry on next class, and we only have 1 module left. Finish up the dewatering and chemical means, and then we can do some review, practice problems together before the exam. Thank you for your time.
Take away the burn load.